All right, so what did we understand through this study? Well, we understood that the chelation is a key factor for this reaction to work, right? You remember that the oxygen-lithium interaction was very essential for the reaction to work. Can we replace the oxygen-lithium interaction by something else? We tried to do these propargylic and homopropargylic amines. That was done with Angeline Chanu, who was a master student with me. Angeline tried to prepare this type of compound because the theoretical calculations had predicted that the chelation should be excellent. Very, very strong interaction between this nitrogen and the lithium. So we thought, oh, if this works, the cyclization should be very quick, and that would be very facile reaction. So we tried that. We prepared this compound, very easy, from commercial butanol, transformed into the corresponding dibenzylamine, and this was hydroxyalkylated by formaldehyde. And of course, the Mitsunobu condensation led us to the starting substrate. So the chemistry was easy at this stage, but unfortunately, we have been unable to do any cyclization with these compounds. The only thing we could do was the iodine-lithium exchange and hydrolysis, reduction of the compound. No cyclization, never. Whatever the nature of the substituent on the nitrogen, whatever the length of the chain here, no cyclization. So there is still something we don't understand. The interaction between the heteroatom and lithium is very important, but there is still something special about acetals that we don't understand, because amines are not able to do the same job. Well, can we extend this chemistry to the construction of six-membered rings? Can we do, for instance, quinones or other type of heterocycles using 2 6-membered rings in a row? So Frédéric Lestrade also tackled this problem. Well, I showed you that with this type of intermediate, we can easily make 4-3-0 heterocycles, such as benzofurane. So there are 2 ways of extending this chemistry. We can introduce 1 carbon on this side to prepare this type of intermediate. And of course, if the cyclization were taking place, we would obtain what we call the chromine skeleton by a 4-4-0 bicyclic system. Unfortunately, the reaction does not work. We have obtained a very, very surprising results with this case. We have obtained, with very good yield, almost 90% yield, this totally unexpected compound. We wondered what kind of chemistry is going on there. A very, very unusual chemistry. So we think that what is going on is that instead of doing the iodine-lithium exchange, we probably do the deprotonation of this position, propargylic position. And if this is the case, there is an elimination of the aryloxy moiety. And this generates an N-in compound with an acetal. And the excess of butyllithium in the medium probably comes to add on the terminal position of the N-in. And this, of course, provokes the conjugated elimination of 1 lithium hydroxide, probably providing this compound. 89% yield, very unexpected. And totally useless also, useless chemistry. What do you want to do with that? Anyway, so we cannot prepare chromine by this chemistry. Can we prepare isochromine? The idea was to add this time a carbon between the aryl and the oxygen. So we prepared this intermediate. But unfortunately, the reaction was even more complex, and no isochromine could be prepared. So it looks like with lithium, we could not do any of these heterocycles. Too many side reactions were taking place. We tried also with isoquinolinones. To do that, we were just starting from the same starting material, and this time transforming this mesylate into an amine and condensing the corresponding amine on this ester, activated ester. We obtained this starting material, which is a benzamide. And this iodobenzamide was treated with an excess of butyllithium, large excess of butyllithium, because we first have to deprotonate the secondary amine, do the exchange, and then the cyclization. Well, the reaction works, but as you can see, the yields are not very, very good. It's difficult to get more than 30% of this transformation. So disappointing, and the selectivity is, well, from medium to good. So we really thought at this stage that lithium was not good enough to do the job anymore. So we had to change metal probably. Well, we thought of the well-known palladium chemistry to do this kind of transformation. We thought maybe palladium would be a much better metal for that. Because, of course, if with palladium we could do the cis-exo-dig cyclization We do not expect the palladium to do the elimination, but maybe in a separate step we could do the conjugate elimination and obtain the final product. Of course, 2 steps instead of 1, but maybe it's worth it. Well, there was a way to do that. That has been described by Grigg, 1988. It's called cyclization anion capture, and the catalytic cycle is the following. So you generate classical palladium 0, you insert it in the carbon-iodine or carbon-bromine bond here. You obtain this kind of intermediate. There is a strong interaction between palladium and the triple bond here. That favors the carbomethylation of the triple bond that takes place here. So you form the carbon-carbon bond, obtain the vinyl palladium. Vinyl palladium are not nucleophilic species. You cannot do that type of chemistry with. But if you have an anion in the medium here, this anion can add on the palladium and eliminate the leaving group Higgs here. And that provides this intermediate. And the reductive elimination of palladium 0 provokes the coupling here. So you can expect the final cyclization to take place with substitution on the vinyl position. The problem is, in this case, can we use this type of chemistry to obtain this type of compound? So that was the challenge. So we tried it. We tried the Grigg conditions, that is using piperidine and formic acid to generate hydride in the medium. The hydride in this case is the nucleophile. And we did this chemistry with this type of compound. You remember that chromium would not work with lithium. So the chromium, we did the palladium insertion. We probably did the cyclization and the anion capture. So we obtained the product, but unfortunately that was not the only product, because probably the hydride capture takes place very early also at this stage, and we obtain also the reduction product. And this 1-to-1 mixture was impossible to separate, exactly the same retention time on chromatography. Furthermore, we tried to provoke the beta elimination on this compound by treating it with tertiobutylithium or Lewis acid conditions. No way to get the elimination product. So there is no way to access to chromium even with palladium chemistry. What about isochromines? Well, for isochromines, the situation is much more favorable. It looks like palladium is doing a very good job. The same conditions provide very efficiently, well, efficiently at least, the expected isochromine compound. And in this case, we use Lewis acid condition with a Unix base to do this beta elimination and get finally the expected product with a bad stereoselectivity, but the chromium at least nucleus could be built by this palladium chemistry. What about isoquinolenones? You remember that lithium could not do this job neither. Well, it works well with isoquinolenone, very well indeed. If we start from the same starting material as before and doing just the protection of the secondary amine, transforming it into a tertiary amine, either methyl or paramethoxybenzyl, we did the same Grigg condition as before with palladium 0 generated in situ. The cyclization is taking place, as you can see, is decent yields. And then a simple heating at reflux of acetonitrile in the presence of formic acid provides the acidic beta elimination of this compound. And we get the final expected isoquinolenones in relatively good yield, but modest stereocontrol of the double bond. So palladium was the good solution for these other heterocycles. What else can we do? Well, I was very, very lucky. In many occasions in my life, I've been lucky. In this case, I've been very lucky because by chance, Muriel Durandetti, who is an assistant professor, left Paris and joined my group. And she was a very good specialist of nickel chemistry. I don't know anything about nickel, but she knew everything. So we tried to apply her chemistry to this problem and see if we could take advantage of it to get some new developments